Okay, so welcome back actually. So we discussed in the previous lecture, we in fact started with the segmentation. We discussed about k-means as an extension to thresholding approach. Then we also started leveraging the neighborhood information with region growing and then region split and merge approaches, right? So hope you are enjoying so far. And before going to the subsequent approaches, in fact, we have a very short approach to discuss in this lecture before we go to an exciting field of graph cuts. Okay, so that's something which is very interesting algorithm. But before going there, I just want to introduce to a website ipol.im. So here what you can get is actually a lot of papers, classical image processing papers with their codes. So in fact, area-wise division is shown here. In signal processing also is there. So let's say features, edges and segmentation. So let's say edge and contour. So if I click, so many of them are there. So you can take one of them and see for, with the code actually. So let's say, I think we'll discuss on snakes and not later. So review of classical edge detectors, let's say. So you can actually go to demo and you can see that actually. So click an image to use it as an algorithm input. So let me just select maybe Barbara to start with, or you can even upload the image. Okay, so now you can actually see with Roberts, Privet, Sobel. So if you apply that bar threshold, you need to put, so anything above will be made as 1, below will be made as 0. Of course, this is normalized. Okay, so RGB images will be converted to grayscale. And then different operators, Mar-Hildreth, we discussed about this, right? With just Gaussian kernels and the logic kernel. So you can actually see that. So results display black on white or white on black, whatever. So just run it. Okay, so take some time. It's running online for you. So you can see here. So input, then Roberts output looks like this. Privet looks like this. Sobel looks like this. Herlich look like this. Mar-Hildreth, wow, that's excellent, right? And log of this one. So you can see log of this and this. So you can set the threshold again here. So you go back, new parameters. If you click, you can set all the threshold here. So interesting, right? I'm very, very striking this one. So that's it. So you just enjoy this page. It's really a very rich treasure as an image processing engineer. So just always keep coming back to this and see what all you can do. Maybe segmentation. I think all these are classical algorithms. You could try it out. Okay, so that's it. So let's come back to the lecture. So we stopped here, in fact, so on the region splitting and merging part. And now I want to introduce something which is very, very interesting algorithm. So we discussed this briefly when we discussed about k-means. Okay, so one thing I was telling you is that we are only worried about intensity. We are not really worried about the neighborhood, right? Now let's combine the neighborhood information along with the intensity and see what we can do. That's exactly what people call as super pixels. So intensity is plus spatial distance. Okay, so the idea here is like regions of image that are contiguous and having similar intensity or color. Okay, so always remember that images that I typically explain in terms of grayscale, but they can be treated in as a color image, and then you need to do it in 3 channels separately. Okay, so that's a major difference. Okay, so what the idea here is you have regions which are coherent. Okay, so gives a more compact starting point for segmentation. So instead of treating every pixel as a separate entity, what you get out of super pixels. So super pixels can be a starting point also. It need not be the end of it. Okay, so you can take the image, you do super pixel algorithm and get super pixels out of the pixels. You get basically some pixels are grouped together because of their intensity and coherence or in neighborhood, and then you can start from there. Okay, for the further segmentation. So that's the beauty about this approach. So instead of starting from millions of pixels, you start from thousands of super pixels. That's the idea. Okay, and keep things together, as I said. Okay, so an example algorithm is an extension of k-means. Okay, so its name is simple iterative linear clustering. Simple iterative linear clustering, SLIC. Okay, so some people call it as super SLIC. Okay, because it gives you super pixels. So this can be on a color image. If it's a color image, it will be treated as RGB channels and XY coordinates. Or it can be 3D in the case of grayscale, where the grayscale intensity and the corresponding locations. So it's a vector. Okay, so that's the thing. And then of course the starting point is initialize the superpixel centers by sampling n locations on a regular grid in the image plane. So that's slightly different from k-means, right? Because k-means, they only care about the intensity. But here what we first start with is you take the image and then we will sample n locations in a uniform regular grid. Okay, so something like, to make it very simple, it's something like this. So you have the image plane, right? You divide it into, so instead of going in each and every pixel, that's what we were saying, you start with small points. Okay, so regular uniformly spaced points. Okay, that's what you go start with, and then move slightly within the 3x3 neighborhood. So again 3x3 is flexible, so but typically it starts with 3x3 to lie on the lowest gradient position. So it's a very interesting algorithm. So you take those n sample grids, okay, and then within 3x3 neighborhood of that, you will go to a new point which is actually having the lowest gradient with respect to the starting point. Okay, so you consider 3x3 directions, all the all the directions possible. Okay, and then you see which one has the lowest gradient direction. So that towards that point you will slightly shift the starting point. Okay, so for example, so let's say, let me use another color. Okay, so let's say, I'm considering this point. So I'll consider the neighbors here, right? Okay, so, and even the other neighbors, and you see in which direction the gradient is minimized. Let's say this is the minimal gradient direction, so this sender will be shifted to here. So that's the meaning of it. Let me just discard all this. Okay, so that's done, and then for each cluster mi, compute the distance between mi and each pixel in a neighborhood of mi. Okay, so now we are talking about intensity. So we started with sampling n locations and then moved to a location which is actually within the 3x3 neighborhood, but on the lower gradient position. The reason why that is, actually we don't want to start on an edge, because from an edge you suddenly have intensity variations on both sides, right? So now what we do is actually considering only these n locations. Now next is on the intensity. So you decide some clusters, just like k-means. Okay, so no different. It's exactly same as k-means, and this will be okay, and compute the distance between mi and each pixel in a neighborhood of mi. Okay, so for each of these cluster you just consider within a neighborhood of mi, and then assign pixel to cluster I if its distance is better than its current value. Okay, so what essentially we started off with is identifying those super pixels, so n locations, and then we will identify some intensity levels. And now earlier what we used to do is, basically in the case of k-means, we used to do for each and every pixel in the image, right? You remember that? And then we were doing the repeat of the same. But here what exactly happens is, we need to calculate the distance. That's one aspect. Okay, and then in fact it is not each pixel, it is each of these n locations. Okay, and there is a distance calculated between the mean intensity, and also it has to be within a neighborhood of mi. So earlier that restriction was not there, because any pixel was considered. But now what we are actually trying to do is, the cluster center is identified. Now we will only consider a neighborhood of that cluster center in terms of its location also. Earlier it was only intensity. So now clusters have some location dependence also. That's a key factor here. And then of course update the cluster. So the distance formula I will explain to you in a short while. What is it actually? So here not only the intensity distance, we have to consider the distance in terms of spatial distance also, actual physical spatial distance also, right? And once that is calculated, update the cluster centers like in k-means. So we were seeing the minimum of the distances and then update the clusters accordingly. The pixel belongs to the one which is the minimum distance one, right? So that's the same thing, same concept is repeated, and again 2 and 3 repeated till convergence. Okay, so in the case of color images, we can actually replace the color of pixels in each cluster with the average, but that's optional. Okay, so the distance is interesting. So this is a 2-factor distance. One is actually of course on the intensity and the other one is on the spatial distance. Okay, so you can see over here in the case of color image, you have the individual channel difference in intensity, and of course you sum it up in terms of square, right? I mean norm 2. And if it is grayscale, it's just the intensity difference like before that we discussed. So the DC factor here is on the intensity, and then this is actually the spatial coordinate distance. Okay, so x, y, I and x, y, j, right? And j here is actually the sort of the centroid, and I here is the superpixel value, the location, right? So just to, if I am confusing you, sorry for that, just to make it very clear. So what we do here is actually not only on the intensity, but we put a restriction on the range of closeness or in terms of physical distance. But an important factor here is actually the DC is in terms of intensity, DS is in terms of pixel distance. So if you want to put this way, this one is in intensity, and this guy is in terms of, let's say, millimeter, right, in pixel distance or number of pixels, let's say. So they have a huge difference among them, right? So we need to normalize that so that they can be added together and be considered as a single distance value, and that is why the C and S factor will come. So they will help us in normalizing the values, the DC and DS values, to such a range that they are comparable, because otherwise DC is measured in terms of intensity and DS is measured in terms of distance, right, the coordinate distance. So in order to normalize that, we use these factors, which is C and S. Okay, so that's it. We'll take an example, the cameraman image. So if I choose some number of grids, the superpixels, that's a parameter in your hand, hyperparameter in your hand, you get something like this. And then if you make all of them uniformly as one intensity, just like the k-means clustering, we get something like this. Okay, let me illustrate this with an example. Okay, so this is the superpixel code. Okay, so here I am reading the image and I have the parameter here 50 superpixels, let's say, and then basically what we do is okay, so it just this is just a code to get the boundaries of these superpixels identified, these clusters identified. Okay, and then of course we can do the mean value operation, where you treat or anything inside that boundary a single value, right? Let me show you so that it's clear. So it's something like this original image. So I identified only 50, right? I put 50 value here. So 50 superpixels are identified, and then entire region is replaced by its mean value. That's all. Okay, so these regions are identified with two constraints in place. Okay, one is basically the what you call the intensity distance, and the other one is the spatial distance. So both are considered in this case. So 50 is the hyperparameter, similar to the number of clusters in k-means, right? We had 5 for example, or 3 for example. So let me increase to 500. Okay, so many pixels. So many superpixels will be considered. Okay, so you can see obviously the number is increased. So instead of having to go through each and every pixel, now I am sort of doing it in only these many levels in terms of intensity and in distance. Both has to be remembered. Okay, so 500 clusters are formed, and those clusters are formed in terms of not only just intensity distance, but in physical distance also, the neighborhood also, neighborhood distance also. So you can see over here, right? It looks really interesting, right? The phase, this is treated similarly, and so on. Okay, now let me change it to the other extreme. Only five clusters are chosen. So you can see over here. So these are the 5 clusters which are chosen, and then you get something like this. Okay, so I hope it's very clear, and this is a very short lecture because now we are going to enter into something which is very interesting, which is more sophisticated segmentation approaches, and that is something known as graph cuts. Okay, so see you in the next lecture.